Hello and welcome to another tutorial on dev.java website. We are looking at the primitive types that Java supports. And we said that we have integer types, byte, short, int, long, and then we have floating point types. These are the fractional numbers, that numbers that have decimal points or decimal digits, float, double, and then we said that be careful about when you're using float or double literals. Be careful about how many digits of precision they allow. We said that float supports only any float literal supports up to 7 digits or 6 or 7 digits. Double is about 17 digits. So if you want the most precise floating point literals in your application, you should define them as double. And we said that that's the reason that Java chose double as the default for the floating point, and same with int. Int is default for the integer literals. And then we have two more basically types that are not directly related to numbers. One is Boolean. Boolean data type has only two possible values, true and false. Use this data type for simple flags that track true-false conditions. This data type represents 1 bit of information, but its size isn't something that's precisely defined, which means that Java language specification doesn't really precisely define what the size of a Boolean is. It's left to the JVM implementation. But we know that, for example, if I go to this primitive one, for example, let's see. So for the Boolean type is just something that has a truth value to it, right? Truth value means it can either be true or false, right? And obviously we use this in a condition, and for example we can say if something is true, do something. So if condition, or for example while condition, right? Whenever we want to make a decision, we have to have some sort of condition to check for its truth value, whether it's true or false, and based on that we make a decision. And in the bytecode you see that, for example, there is a jump bytecode. Same for the CPUs, basically assembly codes. CPUs have a specific instructions to jump, for example, to a specific place in your application in the code. Same for JVM bytecode. It has jump instructions that tell as the JVM executes your application, right? It can jump to different parts of the application based on the conditions. For example, I can say, or let me create actually a new method here. Instead of having the main public static void test1, for example, and then I am going to move all of these previous codes in this one, right? And now we're going to look in the main. We're going to look at so if I say, for example, so let's say I want to say that int a equals 5, right? And then if a equals 7, then do something, sys out, for example, a is 7, right? So this is a condition, and this expression, anything that goes in the argument of the if, has to evaluate to a Boolean type, which means now we can actually assign this expression to a Boolean. So if I say right click on this and source, for example, there should be something to help us extract, for example, refactor, extract local variable, and let's call this condition. And then as you can see, Eclipse automatically realizes as a equals 7 has to be evaluated to a Boolean type. That's why Eclipse defines the type of this condition variable as a Boolean type. Now if we run this, so a is 5. If we say a is 7, then we get a is 7, right? So this condition evaluates to true. Now let's look at the bytecode. So if I open this class file with the class file viewer and look at the so this is the test1 method, and then we're going to look at the main method. So bi push 7. So bi push 7, it says push this 7 to which is an integer, push it to the stack. I store, which means basically store an integer to a location 1 on the stack, or index 1, which is pointing to the address of a variable, which is a. I load 1, and then so this is the first line when we assign a equals 7, right? And then we want to now assign that condition to the Boolean. So a variable with the name condition has been assigned, the memory has been allocated on the Java heap, and the address is saved in the location 2 of the JVM, the stack, right? So, and then we I load 1, it says load the integer from the stack at position 1 on the stack, right, which is a, and then push 7 to the stack, and then if ICMPNE. So this is a jump condition, a bytecode, which means if integer compare an integer, right? We are comparing integers. So I means integer, CMP means compare, NE means not equal, something like that. Yeah. So it says that if compare these two integers, if it's not equal, jump to line 13, and line 13 is basically store 0, icons 0, and note that the Boolean, it returns 0 or 1, right? It says these two icons 1 and icons 0 basically says that if a is, when we say a equals 7, maybe let's see if we can put these side by side. Yeah, I think this is better. And let's zoom in a little bit. All right. So let's see what happens. So we said that these two lines push integer 7. So int a equals 7, it says that push 7 to the stack, because we first have to load the literal number and then allocate some memory and save its address in this variable a, which is location 1 on the stack, right? So that we know that where this variable pointing at, right? Because variable is just sugar coating some memory address. That's why it's easier for in the source code for the programmer to deal with variables instead of dealing directly with memory addresses, which are 64-bit integers, right? And then when we want to assign this, what we do, JVM looks at this if condition and says that, okay, load a, load this, load the value that this memory address, this variable is looking at, and then load a integer literal, which is 7, and then we're going to do a comparison of two integers, right? If ICMP and E not equal. Now, if the condition, so if these are not, so basically what happens is that there is some sort of, I guess, inlining happens. Basically, in the bytecode, what happens here is that the compiler has substituted this basically, so basically a equals 7. If these two are not equal, so we're loading a, we're loading 7, and we check if they're not equal. If they're not equal, we're jumping here. If they are equal, we load 1. So equality, so in the bytecode, Boolean translates into a integer 0 or 1, right? And integer is 32-bit, which is fine. I mean, they're kind of not dealing with 1 byte, so because integer is 4 bytes, but it doesn't matter if you push 1 byte to the stack or 4 bytes to the stack. A stack is 32-bit, right? Or 4 bytes. It doesn't matter. It takes the same, basically the one instruction, right? So it takes one instruction or 1 byte code, whether you load 1 byte to the stack or 4 bytes, which is an integer. That's why they decided to, even for this kind of Boolean operations, they decided to go with 4 bytes on the stack, because it doesn't matter. I mean, the speed is the same. You cannot do any optimization based on that, because the way the stack in the JVM has been defined. So it says that if they're not equal, load 0. 0 means Boolean false, right? If you're familiar with C++, you know that in C++, in C++, actually, when you define a bool variable x, right? 0 means false, any non-zero means true, right? And usually the value that is the default value that used as a non-zero true is 1. That's why here it's loading either 1 or 0 based on whether these two are equal or not, right? It's the same situation here. 1 means that this a equals 7 basically resulted in true. So if it's true, we go to line 14. What is line 14 of the instructions here? Store a condition, integer, I store. It means store an integer into this variable, this memory address, right? And then later, so it stores 1. So if they're not equal, it actually loads a 0, pushes a 0 integer to the stack, and then stores it in a variable named condition, and then loads this condition again, because now we want to use the value. Load means go to the memory address that this variable is holding, and then load the value at that memory address. This is equivalent to dereferencing the pointer, because a variable is more or less like a pointer. It holds a memory address. So it says that this is an integer pointer, this condition. Load an integer. Note that in the source code it's a Boolean, but we said that the way they design the JVM is that it doesn't matter if you load a stack is 4 bytes or 32-bit. It doesn't matter if you push 1, load or save 1 byte to the stack or 4 bytes. It's the same speed. You can never optimize it better than that. So it says that, okay, if these two are not equal, load 0. We jump to 3, line 13, load 0 to this condition, and then or load the integer 0 and then save it in the condition variable, and then load the value that this condition is pointing on, which is 0, and then have an instruction for if equal. Says that now if equal means compare the Boolean to 0. Note that it's different from comparing two integers. If equal means just compare whatever the condition is, or basically the way a stack works. If equal means look at the last value that is loaded into the stack, which was the integer value of this variable condition. If equals means just compare it with 0. And interestingly, CPUs also have this kind of assembly instruction that they can take a value from a register and compare it directly with 0. And it's very fast. Comparing with 0, you just compare the bits, right? So if equal means just compare the last value that was pushed on the stack, which was the value of this condition variable, and compare it with 0. And again, we said that in the bytecode, Boolean is just 0 or 1. That's the way they're treating it. A true value means integer 1. A 0 value means integer 0, right? So they went with 4 byte for Boolean on the stack because there is no speed difference between pushing 1 byte or 4 byte to the stack. And then if equal compares this condition with 0. If it's equal to 0, which means the condition is false, right? If equal means comparing with 0. If the condition is 0 means it's false. Remember, if the false was compare integer not equal. If these two were not equal, the condition becomes false, and we were jumping to 13, which would load 0. So if condition holds 0 means means the condition was false, and then if the condition is false means if we compare it with 0, and if equal to 0, we just jump to instruction 27, which we return. So we never go into the body of the if statement, right? Now let's say we compare these two integers and they are equal. So this not equal instruction returns false, so they are equal. Then we don't jump to line 13, right? We continue. We load we load an integer constant 1 to the stack, and then we go to line 14 or instruction 14. And remember, we push the last value at this point, line 14. The last value that was pushed on the stack is 1, right? Integer constant 1. And then it says that whatever integer that was stored or basically was loaded, stored in a pointer in a variable condition, which is an integer pointer. Basic condition is pointing to a value in the memory that is of type integer. That's why we said that I store. store integer. Remember, all these variables are pointers, and pointers have to have a type. They tell the compiler or the runtime, the JVM, what type they're pointing to. These variables only hold the memory address of those in the Java heap. So it says that store an integer into this pointer, right? And then after that we continue. There is no jump, so we load iload2. iload2 means load an integer which is at the location 2 on the stack, and this is a pointer, so it loads the memory address and then goes to memory address and loads the integer value that memory address has. And then we continue with if equal. So in this Boolean expression translates into these lines of code, right? 6, 9, 10, 13, 14, 15. And then based on what this happens, we eventually end up with the different values in the condition, either 0 or 1, which means condition is either 0 or false. And then eventually we end up with this if statement, which is here. If equal, which means now whatever the value the condition variable holds, compare it with 0. We said that if equal means compare the last value on the stack, which is this condition variable, compare it to 0, directly to 0. And we said that if condition is 0, which means it's false, so we just jump to 27, we return. Otherwise, if it's not equal to 0, we're going to call a static field, get a static, which is Java lang system out. Note that methods are invoked. Whenever you want to call a method, the instruction says invoke. Whenever you want to get a field, you say get, or get a static field, right? Get a static means we're getting a field, which is out of type Java IO print stream. And then after that we LDC, we load a constant, a string, which is A7. So A7 is a string literal, so it loads as a constant of type a string, right? These are string literals are also constants, just like a integer literal, which is a constant. So load LDC means load a constant, which is of type a string, which is A7. And then after that, when we load this and then we invoke virtual, we are invoking a non-static method, which is print line, which takes a string and returns void. So it invokes this, and eventually we hit the return, right? So I hope you really understand how this works, how this if statements and the booleans translates into bytecode. Now obviously when the JIT compiler sees this, it realizes that it can the value of the A never changes, so obviously the value of the condition is always known at runtime. Now if the Java compiler could do better optimizations, it could just look at this, and I mean it could remove the entire thing, because actually if at the moment the condition is true, so basically at compile time the value of A is known, so the Java-C could replace all these lines of code with just saying that, okay, system.out.println, right? Java-C could do that because that's an optimization that happens in the source code, but it decided not to do that. What happens if this condition becomes false? And now look at the main. The bytecode doesn't change that much, right? We load 5, we store it in A, and then load A again, push 7 to the stack because it's a constant literal, and then compare not equal, and if not equal, which means condition becomes false, we load 0 into the condition, and then we load 0, we store it in the condition, and then load it again, and if condition is 0, which means boolean false, we jump to 26 and return. And otherwise everything is pretty much the same, A7, etc. So obviously the compiler could say that, okay, the code ends and we know that the value of A is not changing, so this condition is pretty much false, and really it could just say return, right? All this could be optimized away, but the compiler didn't do that. Now notice what happens if I define this integer as a final. So now it actually went from 0, 1, 2, 3, 4, 5, 8, 11, 13, 16 instead of 26, because now we're giving a compiler a hint that, hey, the value of A is guaranteed not to change. And now the Java C can think a little bit harder and do more optimization, right? It loads 5, store it in A on the stack, and then icons 0. Notice what happened. The compiler at compile time realized that this condition A equals 7 is always going to be false. That's because of this keyword final. So that's one of the best practices when you're doing Java programming. If you define a variable, local variable for example, and you are sure that it's not going to be changed, the value is not going to be changed in the body of the method, mark it as final, because then the compiler can do compile time optimization. Which means that the compiler says, okay, I know the value of A is 5 at this point in time when I'm looking at the source code, and because it's final, it is guaranteed to never change. Okay, and therefore the compiler Java C, which is a dumb compiler, it doesn't do much optimization, but it still has a strong guarantee that this expression A equals 7 is either always true or always false, and it knows that, and it realizes that this A equals 7 is always false, so it just loads 0, which was false, right? So the Java C automatically evaluated A equals 7 to false, 0, and then loads it into the condition, store it in the condition. So the condition, there is no if statement for determining the value of the condition. At compile time, Java C realized that this condition is always false, so it assigns 0 to the false, and then when it hits here, loads the value of the condition, which we know that it's already 0, integer 0, and then it says that if equal, compare it with 0, and then whether we do this print line or we hit, right? So if you mark a variable, local variable as final, it's good. Even the Java C, which is not designed to do any optimization at compile time, is able to do some compile time. Now if you in modern C++, if you are familiar with it, they added this const expr. This is a constant expression. Anything in C++ you mark it as const expr or constant expression will be evaluated at compile time by compiler. So all of these calculations can be optimized. Obviously in Java we don't have such a keyword, so the best we can do in Java is marking everything with final, right? Some people argue that if you are passing parameters or arguments to a method and you are sure that those parameters are not going to be changed, you just want to read the values, mark them as final. Same with local variables. If you define a local variable and you know that the value of this variable is not going to be changed, you're going to use it to do some calculations, but you're not going to reassign this variable, or you're not going to change the value, mark it as final, because a lot of expressions that you do, especially if you compare the value, for example, to a literal like integer, float, double, these can be calculated as at compile time by the Java compiler if you mark them as final, because then the Java compiler has a strong guarantee that the value of the variable is not going to be changed, right? So I hope you really enjoyed this, and please stay tuned. I'll see you in the next one.